13.4 billion light-years away, there's a galaxy blazing with light that's both ancient and, honestly, almost impossible to believe. We're not seeing it as it is today, but as it looked just 290 million years after the Big Bang, when the universe was still just a toddler, only 2% as old as it is now. Back then, things should have been simple. The whole universe stripped down to basics. Just hydrogen and helium, floating around in the dark, waiting for gravity to do something interesting. And yet, this tiny, ridiculously far-off galaxy, just a faint red smudge on the edge of what we can see, is lit up with oxygen. Actual, unmistakable oxygen. That changes everything. Oxygen doesn't just pop into existence. It can't form in a big bang. The early universe didn't have what it takes to make it. You need time. You need stars, big, wild, short-lived stars to be born, burn hot, die in dramatic explosions, and only then throw oxygen out into space. That's the recipe. But if you sit down and crunch the numbers, it doesn't add up. The timing is wrong. According to everything we know about how stars live and die and how long that takes, this galaxy shouldn't be here. Not at this age. Not with these ingredients. Not so far away. Every model, every rule about how the universe gets from simple to complex says what the James Webb Space Telescope found shouldn't even be possible. And yet, here it is. This is where observation doesn't just nudge theory, it blows it to pieces. One discovery, caught by the most powerful space telescope humans ever built, forces scientists to stop, look at each other, and admit that something out there isn't adding up. What Webb spotted in that ancient patch of sky isn't just a record breaker. It's a puzzle box wrapped in starlight, and every time you try to open it, you find another question you never thought to ask. The story starts in a part of the sky astronomers know by heart, the constellation Fornax. Not exactly a glamorous name, but in the world of astronomy, it's kind of a legend. Telescopes have stared at this patch more times than you'd guess. It's been scanned, mapped, cataloged, poked, and prodded over and over again. So when the James Webb, the crown jewel of modern astronomy, 17 years in the making, and parked 1 million miles from Earth, turned its gaze there, nobody expected fireworks. Maybe a few faint early structures. Maybe the wispy ghosts of baby galaxies. Nothing that would make you drop your coffee. Instead, Webb found something that made the whole room go silent. The galaxy shows up in the image as just a tiny red dot. Nothing flashy. Easy to miss if you didn't know what you were looking for. But that color, that deep, saturated red, is saying something huge if you know how to listen. The total lack of blue and green isn't just a random quirk. It's a cosmic signpost. The light from this galaxy started out as ultraviolet and visible radiation, the kind your eyes would normally see. But after traveling for billions and billions of years across an expanding universe, it got stretched, pulled out, redshifted by a factor of 15. So now, those wavelengths are 15 times longer than when they first left the galaxy. By the time that ancient light finally made it to Webb's detectors, it had turned into infrared, light that's invisible to us, but exactly what Webb was made to see. Scientists have a trick for measuring how much the universe is stretched. They call it redshift. Every distant galaxy or quasar gets its own redshift number. This one, it's at 14.3. That number is wild. It puts this galaxy among the farthest things humans have ever seen. Like, ever. In all the years we've looked up at the sky. To really get what that means, try this. Shrink the universe's 13.8 billion years into a single year on a calendar. The Big Bang happens at midnight, January 1st. Today, right now, is December 31st, just before midnight. In that version, this galaxy showed up on January 7th. So, we're looking at something from when the universe was less than a week old, if you count it that way. The cosmic year had barely started. Just think about that for a second. The more you do, the crazier it gets. At 290 million years after the Big Bang, which sounds big, but it's nothing compared to 13.8 billion, the universe was basically a baby. It had just started to cool down after its violent birth. thick clouds of hydrogen and helium, were only just beginning to collapse and form the first stars. The period cosmologists call the Dark Ages, that long lightless stretch after the Big Bang and before stars lit up, had just ended. The universe had only just switched on its lights, and already, somehow, here's a galaxy burning bright, filled with complicated elements that shouldn't even exist yet. Oxygen is the giveaway. It changes everything. It's why this discovery feels like a punch to the gut, in a good way. Oxygen, the third most common element in the universe, the stuff you breathe, the stuff that makes water possible, can't come from the Big Bang. The Big Bang only made hydrogen, helium, and a little bit of lithium. That's it. Everything heavier had to be cooked up later, inside stars, in their hot, crushing cores. Here's how it works. And honestly, the details are the best part. Deep inside a massive star way bigger than our sun, nuclear fusion goes through stages, one after another. Hydrogen fuses into helium. When the hydrogen runs out, the core shrinks and heats up, and helium starts fusing into carbon. Then, when the helium's gone, carbon fuses. Along the way, carbon grabs more helium nuclei and makes oxygen. Each step needs higher temperatures, and each one happens faster than the last. Only really huge hot stars can pull off the whole sequence. And then, the key moment, these stars have to die. Not quietly either. They have to go out in a blaze. When a massive star burns through all its fuel, the end comes fast. The core, held up for so long by the pressure from fusion, suddenly has nothing left to push back. Gravity wins, and the core collapses in less than a second. Meanwhile, the star's outer layers are still falling in when the core bounces, and that rebound drives a shockwave outward at a good chunk of the speed of light. That's a core collapse supernova, one of the most violent things the universe does. In a few seconds, the explosion spits out more energy than the star produced in millions of years. The star is gone, just obliterated. Everything it built up inside oxygen, carbon, neon, magnesium, silicon, iron gets blasted out into space at thousands of miles a second. Those clouds, loaded up with fresh elements, drift out into space and start mixing with the untouched hydrogen and helium all around. Eventually, gravity steps in, grabs hold of that enriched gas, squeezes it together, and before you know it, new stars spark to life out of this chemical stew. These new stars aren't just made of plain hydrogen and helium anymore. Every bit of them carries a trace of what came before, like a birthmark from the previous generation. And when these stars reach the end of their lives and explode in supernovae, they throw even more elements into the mix, adding to the universe's growing library of chemicals. Then, the whole cycle just kicks off again. That's how it works. And here's the catch. You can't speed it up. There's no shortcut. Physics lays down the law on timing, and you don't get to negotiate, just like you can't mess with the speed of light. Now, this is the math that's keeping cosmologists up at night. When you start with the oxygen levels actually observed in this galaxy and work backward, researchers figure it takes somewhere between 3 and 10 full rounds of this stellar birth and death cycle to pile up that much chemical richness. And it's not just the quick life of each massive star. Some of those only live for a few million years. Every round also needs time for the blown-off material to cool down and spread out, for gravity to pull it all back together, for new clouds to collapse, break up, and form brand new stars. The whole process, from a supernova explosion to the next batch of stars lighting up, chews up anywhere from 2 to 20 million years, even if everything goes about as fast as possible. So, crunch the numbers. Say you need at least 3 cycles, and each one takes a minimum of 20 million years just for the gas to collapse and form new stars. That's 60 million years, right there. If it's 10 cycles, which is more realistic, you're talking about 200 million years. But get this, astronomers spotted this galaxy just 290 million years after the Big Bang. And based on what we know, the first stars couldn't have switched on until about 200 million years in, once the Dark Ages ended. That gives you at most 90 million years to fit in all of this. 90 million years for multiple generations of massive stars to form, live out their wild, fast lives, explode, scatter their elements, let those elements cool and clump together, and then go again, over and over. It's not impossible. The math doesn't totally break down. But you need everything to click along at absolutely peak efficiency. No wasted time, no delays, no hiccups. And let's be honest, the universe just doesn't work that way. Not perfectly, not all the time. Nature loves to drag its feet. Delays, slowdowns, feedback loops, they're everywhere. Hot gas from supernovae can actually blast away the gas needed to form new stars, pausing the cycle instead of speeding it up. Turbulence can mess with collapsing clouds. Gravity can pull material in all sorts of directions. Even in our own galaxy, star formation is shockingly inefficient. Most of the gas in a cloud never becomes a star. The rest just gets blown off, heated up, or pushed somewhere else. So for this ancient galaxy to pull off what it seems to have pulled off, either all those usual inefficiencies magically disappeared, or something about the early universe was drastically different from what we think. Or maybe it's some wild combination of both. Figuring that out? That's one of the big puzzles in cosmology right now. To really feel the weight of this mystery, you have to zoom all the way back to the true beginning. Not just the start of the galaxy, or the first stars, but the very first moment of everything. At the start, there was nothing. And then, in a flash that physics can describe but still doesn't totally get, everything burst into existence. The universe was born in a state of unimaginable heat and density. In those first few seconds, matter as we know it didn't even exist. Everything was just a wild soup of quarks, gluons, and other basic particles, smashing into each other in a universe hotter than anything you can picture, billions and billions of degrees. Nothing could stay together. Nothing lasted for long. It was chaos, pure energy, pure heat, raw creation. As the universe grew, it lost heat. That's one of those simple, satisfying facts. As space stretches out, everything gets cooler. Back in those first wild seconds and minutes, the temperature dropped fast, and that's when something incredible kicked off. Quarks started sticking together, forming protons and neutrons, the raw material for atomic nuclei. It was like the universe's first big construction project, happening at a blistering pace. All of this took just 3 minutes. Seriously, physicists have crunched the numbers, and they're sure about it. In that tiny window, the very first atomic nuclei came together. This stretch of time is called Big Bang nucleosynthesis, and it set up the original chemical mix for the cosmos. Hydrogen showed up first, just lone protons, the simplest building block you can imagine. Some of those protons smashed into neutrons and fused to become deuterium, or heavy hydrogen. Deuterium pairs then merged into helium-4, the stablest of the light nuclei. A few traces of lithium popped up from rarer reactions. And then, just like that, temperatures sank too low for nuclear fusion, and the process shut down. 3 minutes, start to finish, the Big Bang's nuclear phase wrapped up in a blink. Here's what was left. About 75% hydrogen by mass, around 25% helium, and a whisper of lithium so little it barely counts. That was it. If you'd checked the periodic table right then, it would have been almost completely blank. Only the first 3 elements existed in any real amount. Everything heavier? Not there. Not even a trace. But even those newborn nuclei weren't true atoms yet. The universe was still way too hot. Electrons' tiny, negatively charged bits raced around, too hyper to settle into orbits around the nuclei. Anytime a nucleus managed to snag an electron, a photon would immediately knock it loose. The whole place was just a hot, dense soup of plasma. Light couldn't travel more than a hair's breadth before colliding with a free electron and scattering. This lasted much longer than you'd guess, 380,000 years, give or take. Finally, the universe cooled enough for electrons to calm down and get captured by nuclei. That's when actual atoms formed. Hydrogen, with 1 proton and 1 electron. Helium, with 2 protons and 2 neutrons in the core, 2 electrons circling. This episode is called recombination, which feels like a misnomer since the electrons weren't reuniting with nuclei, they were meeting for the first time. But the name stuck. Recombination changed everything. Once electrons latched onto nuclei, the fog cleared. No more free electrons meant photons could finally travel unhindered. Suddenly, the universe went from opaque to transparent, and all that trapped light burst out in every direction. That light the cosmic microwave background, or CMB, is still out there, filling the sky with a faint, ancient glow. Whenever you see a map of the CMB, that smooth oval with tiny temperature ripples, you're looking at the universe's first snapshot, taken the moment the fog lifted. But here's the kicker. After recombination, the universe was see-through. Sure, but it was also pitch black. No stars, no fresh light. Just atoms, hydrogen and helium drifting through endless, featureless clouds. Nothing new was shining. Space was cold, dark, and quiet, shaped only by gravity. Tiny ripples in density left over from quantum jitters at the dawn of time made some patches a bit denser than others. These spots pulled in more gas, which made them denser still, setting up a slow but relentless cycle. That's when the Dark Ages began. For a couple 100 million years after the Big Bang, nothing happened that you could actually see. No stars, no fusion, no light, just cold, silent darkness. The universe was basically a collection of gas clouds, inching closer together as gravity did its slow, relentless work. It's a weird time to picture. Matter was out there. Gravity was pulling strings, but there was nothing to look at. If you could somehow float in space back then, during these so-called Dark Ages, you wouldn't have seen a single thing just perfect, endless black. Honestly, it's hard for us to even imagine, since our night sky is packed with stars and galaxies. But things started to build, slowly, in the densest pockets of that darkness. Those gas clouds kept getting bigger. Gravity kept squeezing them tighter. And deep inside the thickest clumps, pressure and temperature ramped up. Then, finally, something snapped. Hydrogen nuclei slammed together hard enough to fuse. Nuclear fusion switched on, and just like that, the first stars lit up. These first stars were different. Pure hydrogen and helium. That's it. No carbon, no oxygen, no iron or silicon. Just the two simplest elements, fusing and spitting out light and heat. For the first time since the cosmic microwave background, the universe made new photons. It was the end of the Dark Ages, the universe's first real dawn. Now, this is where what James Webb found hits you. Those first clean, element-free stars were supposed to burn for millions of years before dying. Only then would their deaths toss out the first heavy elements. Those elements needed time to spread out, mix in, and then give rise to newer generations of stars, each cycle taking its sweet time. According to every model, all of this should have taken way longer than the age of the galaxy we're looking at. It's worth pausing on those first stars. They were wild. We've never seen a true first-generation star, their ancient history, long gone. But we've got models, and they tell a fascinating story. When you build a star out of only hydrogen and helium, you get something that acts nothing like today's stars. Modern stars form from gas that already has heavy elements mixed in, which helps the gas cool, break apart, and form smaller stars. Without those elements, the gas can't cool as easily, so it stays hotter, denser, and collapses into bigger chunks. That means early stars were usually giants. Many were 100 times the mass of our sun, some maybe even 300 times or more. Monsters like that just don't exist anymore. Ironically, it's this massive size that gives us a shot at solving the timing puzzle. The bigger a star is, the faster it burns through its fuel. It sounds backward, but it's true a star 100 times bigger than the sun can live its whole life in just 3 million years, from birth to supernova. Compare that to our sun, which is set to last about 10 billion years, or the tiniest stars, which can burn for 1 trillion years. So, if those first stars were all giants, they'd also be short-lived. If each generation burned out in just a few million years, you could squeeze more generations into a short window. The math gets a little less unforgiving, but it's still tight. But here's where things get really weird. Even if you assume everything went perfectly, the biggest stars, shortest lives, fastest star formation, quickest mixing of elements, the timeline still feels like a stretch. The amount of oxygen we see in this galaxy almost breaks the limits of what could have happened in 290 million years. The universe would have needed to be firing on all cylinders, everywhere, without a single hitch, to pull off what we're seeing. And that's just one part of the story. This galaxy isn't only rich in heavy elements, it's already a full-fledged galaxy, with its own gravity holding billions of stars together in a neat, organized structure. Getting that kind of order takes real time. Gravity needs to gather up gas, clouds have to collapse, stars are born, and all of that doesn't happen overnight. So, the big question is, how does the universe go from a smooth, dark sea of hydrogen and helium to a complex, fully formed galaxy in just 290 million years? That's barely a cosmic blink. These are the puzzles keeping theorists awake right now. This discovery didn't just add another data point, it shoved a new, much tougher question right into the middle of the conversation. Sure, other telescopes have spotted far off, early galaxies before, but never one quite like this, with both this distance and this chemical richness. What Webb found is something of a different kind. It's not just ancient. It's too ancient for how mature it looks. The age and the level of development together, that's what makes this result so jarring. And this wasn't a solo discovery. It took a bunch of observatories and teams, all working together to make sure what Webb saw really holds up. First, Webb grabbed the images and spotted oxygen in the galaxy's spectrum. That spectrum, basically a breakdown of all the galaxy's light, is like a secret code. Each element leaves its own mark, and once you know what to look for, oxygen stands out like a signature. But scientists didn't just take Webb's word for it. Enter ALMA, the Atacama Large Millimeter, submillimeter array, perched high in the Chilean desert. ALMA checked for oxygen at radio wavelengths, using totally different instruments, a whole different approach, and a separate team. And their results matched. When two totally independent methods, using separate technologies, come up with the same answer, that's when scientists start to believe it. That's the kind of proof you need before you start rethinking how the universe works. 3 teams poured over the data. Everyone's numbers lined up. The redshift checked out. The oxygen was there. The galaxy's distance and age? Confirmed. So was the problem. This isn't about some tiny math error or a bit of fuzziness in the measurements. This is a real, deep mystery about how the early universe operated. Either our ideas about how stars form, or how galaxies get enriched with heavy elements, or how fast galaxies can assemble, or maybe even all of those things are missing something big. Before getting lost in the theories, just stop for a second and appreciate what's happening here. Humans, stuck on a small planet, circling a pretty ordinary star, managed to build a telescope that can sniff out the chemistry of a galaxy 13.4 billion light-years away. A galaxy that existed when the universe was just 2% as old as it is now. That alone is wild. The engineering behind James Webb is legendary. A mirror more than 21 feet wide, folded up to ride a rocket, then perfectly unfurled out in space, working at a temperature just above absolute zero, 1,000,000 miles from Earth, catching light that left its source before our sun was even born. What Webb has done isn't just a win for science. It's a testament to what human curiosity and stubbornness can pull off. We built a machine to look back to the start of everything, and now it's showing us things that force us to rethink that very beginning. That's something to be amazed by, no matter how you look at it. Let's dig a little deeper into this puzzle. Sure, the oxygen problem is tough and puzzling, but honestly, that's just the tip of the iceberg. This discovery cracks open a whole mess of bigger questions. Questions at the very core of how we think the universe turned from a bland cloud of gas into the wild, complex, chemically rich place we live in now. We're talking about dark matter, the first stars, how galaxies even form, and whether the cosmic models we've trusted for years are really as sturdy as we hoped. But before we dive into the weirdness, let's get clear on what we actually know about how galaxies come together. If you want to see just how strange this new galaxy is, you need to understand the standard story first. Cosmologists have spent decades building and stress testing the standard model of galaxy formation. Here's the basic idea. After the Big Bang, the universe wasn't perfectly smooth. It had tiny variations in density, little ripples in matter so slight, they were only 1 part in 100,000. These were quantum ripples, born during a sudden burst of expansion called inflation, which happened in a flash right after the Big Bang. Inflation took those microscopic jitters and stretched them out, leaving behind a faint pattern of denser and emptier patches across the whole universe. Now, fast forward hundreds of millions of years. Gravity starts doing its thing. Those slightly denser areas pull in more matter, which makes them denser still, which pulls in even more. It's a snowball effect. Not because the rules change, but because gravity just keeps adding up. Give it enough time, and even the tiniest bump in density can grow into a real clump, a knot of gas, that eventually collapses into stars and galaxies. But here's where dark matter steps in, and it's not a minor detail. The stuff we can see: hydrogen, helium, stars, gas, dust, all the familiar glowing things, is just a tiny slice of what's actually out there. About 27% of the universe's energy is in dark matter, and it's weird. It doesn't shine, it doesn't absorb or reflect light, and we can't see it directly. All we know about it comes from the way its gravity affects the things we can see. Dark matter is basically the scaffolding for galaxy making. While ordinary matter is still cooling off, dark matter has already started pulling itself into these huge, loose structures called halos. These halos form first. Then the regular gas, hydrogen, and helium falls into them. Think of dark matter halos as big, ready-made gravitational wells. The gas drops in, gets squeezed by gravity, heats up, cools down, and eventually forms stars. Without the dark matter halo, the galaxy doesn't have a framework to build on. This whole setup is called the lambda-cold dark matter model, lambda CDM for short. It's the big picture theory that explains how cosmic structures grow, and honestly, it's done a great job. It predicts where we see galaxies scattered across the universe. It nails the patterns in the cosmic microwave background. It even explains why we find clusters of galaxies here and big empty spaces, cosmic voids over there. On huge scales, lambda CDM just works. But the early universe? That's where things start to get shaky. And with this new discovery, one of those shaky spots just got a whole lot bigger. Here's the snag. In lambda CDM, galaxies are supposed to form from the ground up. Small things come first. Tiny dark matter halos collect tiny star clusters. These little galaxies then merge with their neighbors, gradually building bigger and bigger structures. It's a slow, step-by-step process, hierarchical assembly, as the experts call it. So, in this view, the earliest universe, say, just a few 100 million years after the Big Bang, should be a patchwork of simple, primitive things: star clusters, proto-galaxies. At 290 million years, the universe should look rough and unfinished, a draft, not a masterpiece. What Webb's picking up isn't some half-formed galaxy. It already looks like a finished product in a lot of ways. Sure, it's still pretty small, but chemically, it's way more mature than you'd expect for this point in the universe's history. It's already been through several rounds of star formation, and by every chemical metric, it's just further along than theory says it should be. Somehow, instead of the rough draft we expect, we find something that's already been edited and polished. One of the most interesting ideas about why this happened has to do with the very first stars, population 3 stars as astronomers call them. These were made from nothing but hydrogen and helium right after the universe began. Thing is, we've never actually seen a population 3 star. Every star we've ever observed has at least a bit of heavier elements mixed in, because by the time our telescopes could spot them, the universe had already started mixing things up. Those first, pure stars are out of reach now. All we can do is read their fingerprints in the chemistry of later galaxies. The theories about population 3 stars are wild and could be key to understanding what Webb's seeing. For one thing, these first stars were probably monsters, far bigger than most stars that form today. A star a few hundred times the mass of our sun doesn't just burn out faster, it dies in a totally different way. When a star falls between about 140 and 260 solar masses, it doesn't go supernova in the usual sense. Instead, it ends in what physicists call a pair-instability supernova, which is a whole different beast. Here's what happens. Inside these enormous stars, things get so hot and intense that the gamma rays being produced can actually transform into electron-positron pairs, matter and antimatter. That saps the radiation pressure that was holding up the star, so the core starts to collapse. But instead of leaving behind a neutron star or black hole like a regular supernova, this process triggers an insane thermonuclear explosion. The entire star gets obliterated, nothing left, just a massive blast that's even more powerful than a standard supernova. Sometimes, it's like several supernovae going off at once. This kind of explosion matters because it changes how galaxies get enriched with heavy elements. Normally, a supernova throws out some newly made elements, but leaves a chunk behind as a remnant. With a pair-instability supernova, though, the whole star gets blown apart, dumping all its heavy elements into space. That's a huge boost in enrichment efficiency. The next generation of stars can grab almost everything the previous star made. If lots of the first stars died this way, each one would have loaded the surrounding galaxy with the maximum possible amount of oxygen and other heavy elements. That could go a long way toward explaining how so much oxygen showed up so fast. If the enrichment process was that efficient, if every batch of massive stars was completely self-destructing and seeding the galaxy with their entire stock of heavy elements, then fewer generations would be needed to reach the levels we see. The timing feels a little less impossible, even if it's still a stretch. But there's another twist. After one of these pair-instability supernovae, if the galaxy is small and dense enough, all those heavy elements might not drift off into intergalactic space. Instead, the debris could stick around, ready to get scooped up by the next round of star formation almost right away. Early galaxies were probably much more compact than the ones we see today, so this local recycling could have made the process not just efficient, but fast reusing material right there instead of letting it float off into the cosmos. Let's tie this back to another piece of the story: how fast stars popped into existence in the early universe. Right now, in the Milky Way, star formation just sort of chugs along a few new suns worth of material every year. Nothing too wild. But when you look at the early universe, you see a different picture. Some galaxies, especially the starburst ones, were absolute factories. They cranked out stars at rates hundreds or even thousands of times what the Milky Way manages today. So if that galaxy Webb spotted was one of these cosmic powerhouses, if it was tearing through its gas reserves, fusing hydrogen and helium into new stars as quickly as the laws of physics would allow, then everything else would move faster too. Stars would live and die in rapid succession, and all the elements they forged would spread through the galaxy much more quickly. In a starburst, it's not just a supernova here and there. Massive stars explode all the time, dozens, maybe hundreds each year, when things really get going. Each explosion sends out shockwaves that slam into nearby gas clouds, squeezing them tight and jump-starting the next round of starbirth even before the last stars have faded. It's a wild feedback loop. One generation ends, the next begins over and over, much faster than you'd see in a quieter galaxy. Sometimes this feedback gets even more direct. When a big star goes supernova, its shockwave doesn't just heat the gas, it crushes it. If the gas gets packed in enough, gravity takes over, and boom, new stars form. Scientists call this triggered star formation. Here, instead of gas slowly cooling and drifting together over millions of years, it gets slammed into shape in a matter of tens of thousands of years. That's 100 times faster. And honestly, that kind of speed might explain why this galaxy looks so chemically mature so soon after the Big Bang. All these ideas make sense to some extent, but nobody's nailed down a single answer yet. Realistically, it probably took a mix of everything. Big first stars that exploded as pair-instability supernovae, crazy high star formation rates, galaxies hanging onto the rich material from dying stars, and a whole lot of triggered star formation. Everything working in concert to create what Webb is seeing now. Which brings up the elephant in the room. Could the early universe really keep all these processes running at maximum efficiency all at once? There's one more possibility, and some theorists are finally starting to say it out loud now that Webb keeps finding these oddball galaxies. Maybe our problem isn't with how stars form or how elements spread. Maybe it's our assumptions about how things started in the first place. What if the initial density fluctuations, the little ripples that seeded galaxies, weren't quite what we thought? The cosmic microwave background, CMB, gives us an insanely detailed map of those early ripples. It tells us how big they were, how they were spread out, and what the universe looked like just 380,000 years after the Big Bang. From there, our lambda CDM models predict how galaxies should grow and cluster over time, and on big scales, those predictions check out. But what if, at smaller scales, smaller than the CMB, can really show us those density variations were actually bigger than we thought? If those small-scale fluctuations were stronger, then bits of the universe would have collapsed faster and earlier. Dark matter halos could have formed sooner, and galaxies would have had a head start on coming together. That means everything. Star formation, chemical enrichment, all of it could have happened earlier than our models say. Turns out, the universe might have been in more of a hurry than we realized. This is a real, testable idea. As Webb keeps spotting more early galaxies, and it definitely is, piling up a collection of data no other telescope could even dream of, we're getting a better sense of how things looked in the early universe. Their masses, how fast they churned out stars, what chemicals they had, all of that tells us something about the starting conditions. If these galaxies turn out to be more mature than the Lambda CDM model predicts, then clearly the model needs an update. And if that's the case, we'll need to dig into those starting conditions, maybe the physics of inflation, maybe the earliest density fluctuations. That would shake things up. Inflation is a theory that's pulled off some big wins in cosmology, but honestly, we know far less about it than we'd like. We're pretty sure something like inflation happened, but the details, what set it off, how long it ran, what kinds of ripples it made, are still up in the air. If Webb's data forces us to rethink inflation, that change won't just be a minor tweak. It would ripple through everything we think we know about the universe. And then there's the whole dark matter problem. The standard Lambda CDM model says dark matter is cold, slow-moving stuff in the early universe. That's the backbone of the model. It's what lets big things build up from smaller ones. But what if dark matter isn't quite as cold as we thought? Or what if part of it acts a little differently? Maybe it helps build small structures faster, or interacts in weird ways that speed up galaxy formation. These aren't just wild guesses. Over the years, people have come up with all sorts of dark matter candidates. Warm dark matter, self-interacting dark matter, fuzzy dark matter, even primordial black holes. Most of these ideas have been boxed in by observations, but none are totally off the table. Some of them could explain why Webb is seeing early structure that doesn't quite fit the cold dark matter script. So what's really happening with this galaxy? Truthfully, we don't know yet. And that's not a problem. That's the best part of science. When the universe hands you something that doesn't make sense, that's not a crisis. It's an opportunity. Every major breakthrough in cosmology started because something didn't fit. Remember when we found out the universe's expansion is speeding up? That started with supernova data that just looked wrong. Or the discovery of the cosmic microwave background that was two engineers trying to fix a weird hiss in their radio antenna, not chasing after a Nobel Prize. This is how science moves forward. Anomalies. And this galaxy is a top-tier anomaly. The data's solid. Multiple instruments have checked it. It's not a fluke or a glitch, it's a real thing. And it doesn't fit our current playbook. So the playbook will have to change. There's another twist, too. This discovery actually ties into a much bigger question. When could life have started in the universe? At first, it sounds like a leap galaxies to biology, but it tracks. Life doesn't just need hydrogen and helium. It needs all the other elements: carbon, oxygen, nitrogen, phosphorus, sulfur, the building blocks for living molecules. Those weren't around at the start. They had to be forged inside stars and spread around by exploding supernovae. For a long time, people assumed the universe needed billions of years of star building before life had any shot at existing. The idea was pretty straightforward. In the universe's early days, things were just too raw. No real chemistry, nothing for life to work with. So, for the first few billion years, the cosmos was basically a construction zone, busy assembling the elements life would eventually need. Our solar system didn't even show up until the universe was already 9 billion years old. In that story, we're latecomers, inheriting 10 billion years worth of cosmic handiwork. But then along comes Webb, spotting galaxies pumping out oxygen plus, probably, carbon, and other building blocks, just 290 million years after the Big Bang. Suddenly, the chemical toolkit for life was coming together way sooner than anyone guessed. This doesn't mean life itself sprang up right away. The path from simple oxygen in a young galaxy to something alive is ridiculously long and complicated. Still, the universe started laying out the raw ingredients for life much earlier than the old story ever allowed. That leads to a wild question. Could life have popped up somewhere in the universe far earlier than we thought? Not necessarily life like us, or even life on a cozy little planet orbiting a sun-like star. But what about some weird early chemistry? Something self-organizing, processing information, getting just complex enough to count as life. We don't have the answer yet, but now it actually feels worth asking. Webb's discovery also shakes up the usual timeline astronomers use for star formation. The basic picture goes like this. Star making took off fast after the Big Bang, peaked about 2 or 3 billion years in what scientists call cosmic noon, then slowly petered out. Most stars formed during that early, hectic stretch. For the last 10 billion years or so, the universe has been coasting, making stars at a much slower pace. But if galaxies were already churning out stars just 290 million years after the Big Bang, way before cosmic noon, then something's off. Maybe the early growth in star making was steeper than we thought, or maybe the whole peak happened sooner. Either way, the timeline needs an update. And changing the star formation story means changing the chemical history, which changes when planets can form. And in the end, it all shifts the way we think about where and when life might show up in the universe. Everything's connected. That's one of the big takeaways from modern cosmology. Tug on one thread, and the whole tapestry moves. And the thread Webb just handed us? It stretches for 13.4 billion light years, no exaggeration. Now, about that Redshift 14.3 number, let's break it down, because the jargon hides just how mind-bending it is. When we say a galaxy is at Redshift 14.3, we mean the universe has expanded by a factor of 15.3 since the moment that light left. Back then, the universe was 15.3 times smaller than it is today. Everything, every distance, between every point was squashed together. The galaxy we see now as being 13.4 billion light years away was, when its light started traveling, much closer to where our own galaxy would eventually form. This isn't just a fun fact, it matters, because it shows how radically different the early universe was. It wasn't just younger or simpler. It was denser, hotter, and jam-packed. Galaxies were crammed closer. The cosmic web of matter was all squeezed into a tiny volume, and the whole place was buzzing with energy. At 290 million years after the Big Bang, the universe was a totally different kind of place than what we see now. When matter is packed tighter, gravity gets stronger. That makes gas clouds collapse faster. And when that happens, stars form more quickly. That's actually part of why the early universe churned out stars at such a furious pace, at least for each chunk of space. Back then, the gas was denser, easier to gather, and gravity had a much easier time pulling it together into new stars. Everything about the environment favored fast, intense bursts of starbirth. But all that energy came with a price. The early universe was chaotic. Lots of nearby supernovae throwing out hot gas, radiation, and violent winds, constantly stirring things up. Out there, the tug of war between building up stars and tearing them apart played out in a way we just don't see anymore. Trying to capture all that in a model is a nightmare. This is why simulations of early galaxy formation keep running into trouble. To really nail down what happened, you'd need a ridiculous amount of computing power enough to track both the grand sweep of gravity and the nitty-gritty details of gas clouds collapsing or supernovae exploding. We've made big strides, sure, but there's always a trade-off. Simulations rely on recipes they stand in for the messy reality of star formation and supernova feedback with statistical shortcuts and rough approximations. That sort of thing works okay for the more recent universe, where we can check our models against a mountain of observations. But for the early universe, we've mostly been guessing with barely any data to keep us honest. Now, thanks to the Webb telescope, we're finally getting a look, and some of our simulations just aren't holding up. Webb is catching galaxies that are bigger, more evolved, or more common than we thought possible. The galaxy at Redshift 14.3 is an especially wild example, but it's not alone. Webb keeps turning up surprises, so the theorists are scrambling. They're tweaking their models, adding new physics, overhauling how they handle star formation and supernova feedback, whatever it takes. That's how science is supposed to work. You make a prediction, reality pushes back, and you adjust. But there's a nagging thought some folks are starting to say out loud. What if it's not just a matter of fine-tuning star formation or supernova recipes? What if there's something deeper, something off, with the basic story we've been telling about how the universe works? The standard model, Lambda CDM, has been a workhorse, but it's not perfect. There are cracks. The most famous is the Hubble tension, a mismatch between the rate of cosmic expansion measured from the early universe, the CMB, and from nearby galaxies. The numbers are close, but stubbornly refuse to line up, and nobody's been able to fix it. Some people blame systematic errors. Others think maybe it's a sign we're missing a key piece of physics. There are other oddities too. The way matter clumps, the number of tiny galaxies orbiting big ones, and now these unexpectedly massive galaxies showing up early on. None of these problems, on their own, break the model. Each one could have a mundane explanation. But the list keeps growing, and every time we look closer, we find something else that doesn't quite fit. It's got some cosmologists wondering if all these little puzzles add up to a bigger one, a gap in our understanding that we haven't managed to spot yet. Let's get clear about what's really going on here. This doesn't mean our whole understanding of the universe is wrong. The basics, the Big Bang, the universe expanding, dark matter, dark energy, and how things clump together because of gravity are rock solid. Tons of evidence points to them from all sorts of directions. No one's throwing those out. What's actually happening is, the model looks incomplete. Maybe we've missed some physical process. Maybe there's a piece of the puzzle we haven't plugged in yet. Something about how the universe behaved in its early years just isn't lining up with what we thought. But honestly, an incomplete model can still do amazing work. Physics is full of examples like that. Take Newton's gravity, it nails everyday stuff, but Einstein showed us where it falls short. Or look at the standard model in particle physics. It's the most thoroughly tested theory ever, but we know it leaves out gravity, dark matter, and dark energy. Being incomplete doesn't make a model useless. It just means we have to recognize what's missing and keep looking. That's exactly what Webb, and this discovery in particular, is helping us do. It's showing us where our current ideas start to wobble. And that's a huge deal for science, not because it destroys what we've built, but because it tells us where to go next. So, what's next? Well, this isn't the end of the story. It's a jumping off point. Scientists are already digging in, and the pace is only going to pick up. Right away, people started searching for more galaxies like this one. If the early universe was further along than we thought, this galaxy can't be the only one. There should be more, maybe a lot more, at the same age, or even older, with just as much chemical complexity. Webb is on the job, running survey after survey, and the list of ancient galaxies keeps growing. Patterns are starting to show up. And here's what those patterns are saying so far. The early universe has more grown-up galaxies than the standard lambda CDM model predicted. It's not just this one oddball. We're seeing it happen across different ages and groups of galaxies. We're not at the point where we can say the standard model is busted, but it's clear something interesting is happening that we haven't nailed down. Theorists are all over this. Some are going back to the drawing board with the first stars wondering if they were bigger, died in new ways, or gave off different feedback than we thought. Others are tweaking dark matter, trying to see if changing its properties could explain galaxies showing up sooner. And some are messing with the starting conditions, seeing if models of inflation could give us more small-scale structure early on. Observers are charging ahead too. Webb is zooming in on the most promising early galaxies, collecting detailed spectra to figure out not just how far away they are, but what they're made of, how fast they're forming stars, how massive they are. All the stuff that helps us sort out which theories fit. ALMA is jumping in with radio observations, looking at cold gas, dust, and how these galaxies move. And soon, the new generation of giant ground-based telescopes being built in Chile and Hawaii will add even more firepower. The 30-meter telescope, the Giant Magellan Telescope, the Extremely Large Telescope. These monsters won't replace Webb, but they'll give us new angles, different wavelengths, sharper details. Together, they'll create an incredible toolkit, letting us examine the early universe in ways astronomers a generation ago couldn't even dream of. As we push deeper into the universe, this galaxy at redshift 14.3 stands out. It's not just another data point. It's a real test for any theory about how galaxies formed in the early days. No one can brush it off as a mistake or some weird outlier. The evidence is just too good. Every instrument, every method lines up. This galaxy exists, and honestly, it's just as remarkable as it looks. There's something kind of profound about how this discovery messes with our sense of cosmic time. We usually picture time as this resource the universe uses up to build complexity. More time means more chances for things to happen, for stuff to come together, for chemistry to get interesting. The universe needed time to make stars. Stars needed time to cook up heavy elements. Those heavy elements had to scatter and mix before new stars and planets could form. Time was like the currency of cosmic evolution, and we always figured the early universe barely had any to spend. But here's the twist. This galaxy is telling us the early universe was way more efficient with its time than we thought. It figured out how to cram what we figured would take hundreds of millions or even billions of years into a tiny slice of time. It spent its time budget with a kind of speed and resourcefulness our models just didn't see coming. And honestly, we still can't explain how it pulled it off. That realization sends ripples everywhere. Think about what it says about cosmic age. When astronomers say the universe is 13.8 billion years old, they're not just guessing. They've got all these independent ways to check how fast the universe is expanding, how old the oldest stars are, the patterns in the cosmic microwave background. All those lines of evidence point to the same answer. The age isn't in doubt. It's as solid as almost any number in science. But this discovery doesn't mess with the universe's birthday. It messes with our ideas of what could happen at certain points along the way. We thought we had a handle on the pace and order of events in the early universe. Turns out, we might be way off when it comes to what happened right at the beginning. Picture this. You find a document, and it's clearly dated just 20 years after the founding of a civilization. But in it, you see advanced metalworking, complex laws, sophisticated farming stuff you'd expect would take centuries to develop. The date isn't wrong. The civilization is real. The techniques are there, but your whole idea of how civilizations grow just isn't lining up. Either development can happen way faster than you thought, or maybe the conditions were just totally different than what you expected, or maybe it's a bit of both. That's kind of where cosmologists are now. The age of this galaxy? Not up for debate. The oxygen? It's really there, but the models need some work. And honestly, that's what makes this moment so exciting. Not just technically impressive, but genuinely thrilling the way the best scientific discoveries are. The Webb telescope has only been running for a few years. Its deep dive into the early universe is just getting started. Every new high redshift galaxy they confirm, every new bit of data, sharpens our picture of what the early universe really looked like. Each new observation is a challenge to theory. Every early galaxy web finds either lines up with our models or blows right past them. Every measurement, chemical makeup, star formation rate, mass, it's all a test, and that's how science moves forward. Theories that pass get stronger. The ones that don't get tweaked or tossed. Sure, it's a messy process. Scientists have careers and reputations staked on these models, but at the end of the day, the universe doesn't owe us tidy answers. Our models have to fit the universe, not the other way around. That galaxy at Redshift 14.3, honestly, it's one of the clearest hints so far that something in our understanding needs to shift. But let's dig into the oxygen part, because there's more here than just a simple timeline of chemical enrichment. Sure, astronomers detected oxygen in this galaxy, but what they really picked up was an emission line, a specific color of light that pops out when oxygen atoms have their electrons jump between energy levels. This isn't just a box check for oxygen exists. This kind of spectral signal tells you about the gas itself, how hot it is, how dense, and how much radiation is blasting through it. The particular emission line they saw is called OII. It's a strong one, a real standout, and you get it when oxygen is doubly ionized, meaning the atoms lost 2 electrons thanks to a flood of intense radiation from massive young stars. When those stars form, they light up their neighborhoods with ultraviolet light. That energy tears electrons off hydrogen and oxygen atoms, and then, as the electrons find their way back, you get these sharp, colorful fingerprints. OIII is one of the brightest of these, especially in places where stars are forming like crazy. And the punch of that OII line? It basically tells you how fierce the star formation is. Strong OII means loads of big, hot stars pumping out UV light. This galaxy at Redshift 14.3 shows a seriously strong signal, so we're looking at a system that was busy, not sleepy or drifting along, but rushing ahead, churning out new stars at a wild pace for its size. Everything else we know about this galaxy fits that picture. It's in the thick of a starburst, one of those moments when a galaxy makes stars way faster than the Milky Way does now. We're not seeing a finished product here. We're catching it mid-chaos, burning through its gas, building stars at a clip it can't keep up forever. Starbursts don't last. The gas runs out. When a galaxy burns through most of what it's got, the star formation rate crashes. All those hot, young, blue stars, the ones lighting up the OII line, die off in just a few million years. With no new ones taking their place, the galaxy fades, shifting toward the dimmer, redder light of old stars. What happens after? No one really knows. It might collide and merge with other galaxies, get a fresh shot of gas, and kick off new star formation. Or maybe it just settles down, its stars aging quietly. Maybe it even becomes the heart of a much bigger galaxy over time. But we can't watch its future play out. When we look out into deep space, we're looking back in time. We're seeing this galaxy as it was 13.4 billion years ago. What it is now, that's a mystery. It could be out there somewhere, blended in among the nearby galaxies, its ancient beginnings lost in the crowd. That's a strange thought, honestly. Somewhere in the universe as it exists right now, maybe not all that far from us, in cosmic terms, there's a galaxy that used to be the one we saw at Redshift 14.3. It's aged more than 13 billion years since then. It's probably collided with others, maybe a bunch of times. It's seen endless cycles of stars being born and dying. The oxygen we detected way back then is still out there, locked up in stars, planets, or drifting through clouds of gas that have long since moved on from that first wild burst of creation. The atoms aren't gone. They're scattered, but they're still here. Here's one of the wildest things about cosmic evolution. Atoms stick around. Once they exist, they don't just vanish. Take oxygen, for example. Some of the oxygen atoms floating around today were born inside a massive star more than 13 billion years ago. Since then, they've moved from one generation of stars to the next, drifted through vast molecular clouds, and even ended up inside planets. In some corners of the universe, those same atoms have probably joined water molecules on alien worlds. The specific oxygen atoms the James Webb Space Telescope picked up way out in a distant galaxy are still out there, doing their thing somewhere in the universe right now. The chain that links that ancient moment to today hasn't broken. It's made entirely of atoms. And honestly, this is where things get a little emotional if you don't mind a quick philosophical pause. Given what's at stake, I think it's more than fair to take a step back and think about what this really means. We're made of the universe. That's not just some nice poetry. It's literally true. Every single atom in your body was forged in the heart of a star. The hydrogen in you came from the Big Bang itself. But the carbon in your DNA, the oxygen you're breathing, the calcium holding your bones together, the iron in your blood, all of that was built inside stars that lived and died, long before our solar system even formed. Our sun and its planets came together from a cloud of gas and dust that had already been enriched by the ashes of countless earlier stars. Earth formed from that stuff. Life got going because of that chemistry. So, in a direct, physical sense, we're the descendants of those first stars. The oxygen those ancient, massive stars made, like what Webb detected in that far-off galaxy, became part of a chemical legacy that's carried forward ever since. Each new generation of stars took that legacy, enriched the universe a little more, and then died, spreading their elements even further. That's how we end up with the chemical richness we see in the universe today. And we're part of it. We're walking, thinking collections of stardust, shaped over billions of years into creatures who can build telescopes and wonder where we came from. So when the James Webb Space Telescope picked up that oxygen signal from an ancient galaxy, the universe was, in a weird way, looking at itself. The atoms in the telescope's detectors, the electronics, the scientists doing the analysis, even the whole civilization behind all of it, traces back to the first stars. The telescope was peering at its own ancestors, so were we. And what we found is that those ancestors were older and more complicated than we guessed. The story of how we got here is messier, richer, and way more surprising than we thought. That's kind of a lot to take in. But let's get back to the nuts and bolts, because there's more science here that deserves some attention. One thing people sometimes overlook is what this discovery tells us about galaxy mass and chemical enrichment in the early universe. In today's universe, it's clear. Bigger galaxies usually have more heavy elements than smaller ones. That checks out. Big galaxies have stronger gravity, so it's harder for supernova explosions to blow away enriched material. Plus, they've made more stars over time, which means more chances to crank out new elements. Astronomers call this the mass-metallicity relationship, and it's one of the most solid patterns we see when we look at galaxies. Back when the universe was young, the usual link between a galaxy's mass and its metal content just doesn't seem to work the way it does now. Take this galaxy at Redshift 14.3. By today's standards, it's small and not very massive. Still, it's packed with heavy elements enough that we can spot them easily, enough that you'd need several rounds of massive stars living and dying to account for it all. If a galaxy like this is so low mass, yet so enriched, then clearly, something about how galaxies made metals back then doesn't match what we see today. Maybe in those first galaxies, mass and metallicity weren't tightly linked yet. Early galaxies were just starting to pull themselves together, gathering mass and deepening their gravity wells. If one of these little galaxies managed to burn through its gas and make stars at a wild pace, it could boost its metal content fast, even if it stayed small overall. The how and how much of metal production probably depended a lot more on chance, on what was happening locally, than on any neat, predictable trend. Things were just messier back then. And this randomness isn't just speculation. Webb's growing pile of data is starting to put this idea to the test. If early galaxies really did evolve in a more chaotic, unpredictable way, we should see a bigger spread in their properties at high redshift. Not the tidy, almost boring relationship between mass and metal content we see now, but a jumble, some tiny galaxies loaded with metals, some barely enriched at all, each following its own path, depending on how its stars formed and died. Early results from Webb are pointing in that direction. The spread in galaxy properties is bigger. The outliers stand out more. The early universe just wasn't as uniform or predictable. It was full of dramatic extremes. Honestly, that fits. The early universe was denser, everything was happening faster, and tiny differences in starting conditions got blown way out of proportion. If one patch of space collapsed just a little earlier than its neighbor, it didn't just get a head start, it could race ahead, form a whole generation of massive stars, and enrich its gas before the next patch even got going. These feedback loops between star formation and chemical enrichment are wild and nonlinear. Small tweaks at the start could lead to huge differences in the end. Now, with billions of years gone by, galaxies have had time to smooth things out. They've merged, swapped gas, and averaged out their messy beginnings. Things have settled into a sort of statistical calm. But back then, every galaxy was like its own isolated experiment, and every outcome depended on its unique starting point. That galaxy at Redshift 14.3, maybe it's just one extreme result, a system that, thanks to luck or the right mix of conditions, managed to get rich in metals at lightning speed. And that leads to a wild question. How many more galaxies like this are out there? Is this one a cosmic fluke, a rare oddball? Or is it the tip of the iceberg, a sign that there's a whole population of fast-evolving, chemically advanced galaxies we just couldn't see before Webb? The answer matters. If these galaxies are rare, we might just need to tweak our models a bit, maybe adjust how efficiently early stars formed, or rethink some types of supernovae. But if they're common, if Webb keeps finding more at similar redshifts, then we're missing something big about how early galaxies formed, and the whole picture might need a serious update. Right now, it looks like we're in the middle. Webb's showing us that the early universe had more developed galaxies than anyone expected, but not so many that we have to throw out everything we thought we knew. The galaxy at Redshift 14.3 is still an outlier, even among its peers, but it's not completely alone. There are other galaxies in Webb's data that are too big, too bright, too chemically mature for their age. The trend's taking shape. The early universe keeps surprising us. How much it does, and what it all means, that's still up for grabs. Let's step back for a second and think about what just happened. Astronomers found this galaxy in the Fornax constellation, a patch of sky that's been picked over, again and again, for years. That's not just a footnote. It says a lot about what our new tools can actually do. Remember the Hubble Space Telescope? For decades, it was the gold standard. Hubble stared at Fornax for ages, gifting us the iconic Hubble Deep Field and Ultra Deep Field images. Those photos changed everything. Suddenly, thousands of galaxies came into focus, and we saw farther into the universe than we ever had before. But Hubble has its limits. It's built to see in optical and ultraviolet light. The oldest, farthest galaxies, their light has shifted way out into the infrared so far. Hubble just can't see it. No amount of staring or number crunching would fix that. There's just a wall you can't get past with Hubble. Webb was built to climb over that wall. Bigger mirror, finely tuned infrared detectors, and stationed far from Earth's own glow. All of it designed to catch the light Hubble simply misses. When Webb aimed at the very same patch of sky Hubble had already studied to death, it pulled out objects Hubble never stood a chance of seeing. Not because Hubble screwed up, but because physics just made those galaxies invisible to it. This is a good moment to remember something about astronomy. Every time we build a new kind of telescope, a machine that sees in a different part of the spectrum, or from a new vantage point, we find stuff we didn't even know we were missing. Early radio telescopes found pulsars, quasars, the cosmic microwave background stuff that was invisible to optical scopes. X-ray telescopes caught neutron stars and black holes gulping down gas, clusters glowing in X-rays. Infrared telescopes started to show us a universe stuffed with dust and newborn stars. Webb isn't the finish line. It's just the latest leap forward. Someday, the telescope that replaces Webb will do the same thing, open another window, show us something unexpected. That's how it always goes. Every time our vision widens, the universe turns out to be even more tangled and astonishing than we thought. There's no reason to think that's going to stop. But for now, this is Webb's moment. And what it's showing us is wild a galaxy at the very edge of what we can see, shining with signs that generations of huge stars have already lived and died there, in a time when our models barely allow for that kind of chemical richness. It's a message from the dawn of time, written in the light of oxygen atoms blasted by the energy of young stars. It'll take years to fully decode all this, but the work's already started, and the first results are jaw-dropping. Just think about the scale for a second. The photons Webb picked up from this galaxy started out 13.4 billion years ago. Back then, that galaxy was a tiny, frantic star factory in a universe 15 times smaller than today's. Those photons spent all that time crossing a universe that kept stretching and stretching beneath them. Their color got dragged out from ultraviolet all the way to infrared. By the time they hit Webb's detectors, they were exhausted travelers, carrying stories from an age before our sun, before our galaxy, before almost anything familiar had even begun. When photons from that ancient galaxy finally hit Webb's detectors, they turned into a stream of electronic signals. We beamed those signals down to Earth, ran them through computers and software, and then handed them off to scientists who used hundreds of years of physics, chemistry, and astronomy to figure out what they meant. Think about that chain for a second, from an oxygen atom flickering in a galaxy billions of years ago, all the way to a research paper trying to crack a cosmic mystery. It's honestly one of the wildest feats of information transfer in the universe. That signal traveled 13.4 billion light years and 13.4 billion years just to reach us. And not only did we build a machine to catch it, we built a civilization that could understand it. That's incredible. Seriously. If you take nothing else from this, just sit with that for a minute. But let's zoom out a bit. Webb hasn't just been chasing one galaxy, it's been racking up discoveries that are shaking up what we thought we knew about the early universe. Webb wasn't built to answer just one question. It's an observatory, a Swiss Army knife for the cosmos. It looks at planets right here in our solar system. It watches new stars being born in the Milky Way. It studies the atmospheres of planets circling other suns. It checks out galaxies near and far, young and ancient. No other space telescope comes close to its range. Still, the most jaw-dropping results so far? They've come from Webb's look at the early universe, those galaxies from the universe's first billion years. This is where Webb really changes the game, because Hubble just couldn't see this far or this deep. Every time Webb peers into the cosmic dawn, it finds galaxies that are bigger, brighter, and more mature than anyone expected. This isn't just a minor statistical blip or a little bump in the numbers. Again and again, Webb turns up ancient galaxies that look way more evolved than our old models ever predicted. It's so consistent that scientists are writing papers with titles that basically say, "Our galaxy formation models are broken. The astronomy community is taking this seriously." The old theories are under real pressure now, and with every new Webb discovery, that pressure ramps up. Now, the galaxy at Redshift 14.3? That's the real outlier. It's the one that sticks out the furthest from what our models say should be possible. If you plotted all these surprising early galaxies, this one would be the farthest from the pack, the one that demands we rethink everything most urgently. At the same time, this galaxy isn't just a problem, it's a clue. Its size, its brightness, its chemistry, how fast it's making stars. Each of those details narrows down what could possibly explain it. If someone comes up with a theory involving huge first-generation stars to explain its chemistry, that theory still has to match the galaxy's brightness and size. If another theory says star formation happened insanely fast, it still needs to fit the oxygen levels and the weird emission lines we see in its spectrum. The point is, the data isn't just a puzzle. It's a puzzle with jagged, oddly shaped pieces, and the solution has to fit all of them at once. That's why Webb's spectroscopic powers matter so much. Instead of just snapping a picture, Webb spreads the galaxy's light into a rainbow and measures exactly how bright each color is. Those emission line ratios tell us how hot and dense the gas is. The width of the lines shows us if the gas is swirling in an orderly way or just chaotically turbulent. The mix of chemical elements reveals the specific story of how stars inside that galaxy forged heavier elements. Every measurement narrows down the options, and the right theory has to make all the pieces click together. Spectroscopic analysis of this galaxy shows more than just oxygen. We're looking at a young galaxy, bursting with star formation, in conditions that just don't exist anywhere in the universe today. The radiation blasting through its gas is fierce, the kind you get from huge, scorching hot newborn stars. Its gas is packed in tight, which fits with the idea of a compact system. And when you look at how the gas moves, it's messy and unsettled. Nothing like the smooth, organized spinning of mature galaxies like the Milky Way. Put it all together and you get a wild scene, a galaxy caught in the chaos of its earliest days, growing up fast and loud. It's a good reminder that galaxies have their own life cycles, almost like living things. This galaxy at Redshift 14.3 is just a baby, but what a wild, overachieving baby. In just a few 100 million years, it's managed feats we expected to take billions. Now, we're left wondering, is this kind of breakneck growth normal for early galaxies, or is this one just an outlier? That's exactly the kind of question the Webb telescope is trying to answer right now. We've come a long way together in this story. Think about it. From the very beginning, before even the first stars flickered on, through those long, dark stretches of silence, right up to the explosive births and deaths that scattered the universe's first heavy elements. And now, here we are, staring at a tiny red dot in an infrared image from the most powerful telescope humans have ever built. Inside that speck of light is a chemical secret that's thrown modern cosmology for a loop. So, let's pull it all together. Let's look at what we truly know, what we're still guessing at, what we're hoping to learn, and what this all means not just for science, but for that bigger, older human story about figuring out where we came from and how we fit into this wild, ancient universe. First, what's this discovery actually telling us about how quickly the cosmos changed? Here's the thing that keeps popping up. No matter how you look at it, everything moved faster in the early universe than we thought possible. Not just a little faster, a lot. Take this galaxy at Redshift 14.3. The chemical complexity it reached should have taken way more time, at least according to what we know about how stars live and die and how elements spread. But there it is. It happened. The universe just made it work. But what does that mean exactly? It means that the basic processes, the birth and death of stars, heavy elements spreading out, new stars forming from enriched gas, either happened more efficiently than we guessed, or the rules weren't quite what we assumed, or maybe both. The universe didn't break the laws of physics. It never does. Every single thing that happened in that galaxy followed the same rules that run the whole show: quantum mechanics, gravity, nuclear fusion. The laws are solid. It's our understanding of how those laws play out, especially under the wild conditions of the early universe, that needs some work. That's an important point, and it gets lost sometimes. People love to say discoveries like this mean the universe broke the rules, or that physics is wrong. But that's not it. We got the laws right, but maybe our math about what those laws should do in the early universe was off. Our models are just best guesses, built on a bunch of assumptions. Some of those assumptions might not hold up when things get really extreme. When you've got enormous, first-generation stars, pure chemistry, intense radiation, all packed together. Now, the job is to figure out which assumptions need fixing and why. One of the best ways to look at this is through what astronomers call feedback. Basically, how star formation changes its own environment, which can either help or stop more stars from forming. Feedback is huge in galaxy formation, but honestly, it's still one of the trickiest things to pin down. We know it happens, we can see the effects, but how does it really work? On what scales, how quickly, how efficiently, and under what conditions? That's where things get hazy, especially in the most extreme early galaxies. Positive feedback, where one burst of star formation sets off another, might help explain why things went so fast in this galaxy. Think supernova shockwaves, squeezing gas into new stars, or the radiation from massive newborn stars pushing gas into dense shells that then break up and make even more stars. Or maybe the gas just cooled faster and more efficiently back then than it does in today's quieter universe. All of these things could have sped up the cycle, turning a process that usually takes tens of millions of years into something much quicker. Negative feedback, in other words, the way star formation heats or kicks gas out of a galaxy and slows down more star formation, usually stops galaxies from turning all their gas into stars right away. Supernovae blast hot winds into space. Young stars heat up the gas around them and shove it outward. These things keep star formation in check in most galaxies today, so stars don't just pop up everywhere all at once. But early galaxies were a different story. They were so dense and compact that gravity held onto their gas much more tightly. Negative feedback just didn't work as well. Instead of blowing the gas out into space, gravity kept it close. That meant galaxies could recycle their gas quickly, fueling a much faster and more efficient cycle of star birth. If negative feedback was weaker and positive feedback worked better in those early times, both pretty reasonable guesses, given how extreme things were, then stars could have formed faster, with less wasted material. The whole process of enriching the galaxy with new elements would have happened in a much tighter time frame. So maybe the weird galaxy astronomers just found isn't some strange outlier after all. Maybe it's just what you'd expect from those wild early universe conditions. Honestly, that's the hopeful take hopeful, because it doesn't mean we have to throw out our basic understanding of physics or the cosmos. We just need to tweak the details of how feedback works under those extreme conditions, not rebuild everything from scratch. That'd be a relief for a lot of cosmologists who've spent years working on the standard lambda CDM model and would really rather not see it collapse. But you can't ignore the less comforting possibilities either. Maybe the universe's initial conditions, the way tiny density ripples were set up by inflation, were actually different than we thought. The cosmic microwave background pins down those conditions really well on big scales, but when it comes to the tiny scales that matter for making the first galaxies, we don't have such tight constraints. If there was more power on those small scales than we expect, then galaxies would have formed sooner and grown faster, making discoveries like this one less surprising. That's one of the big reasons researchers keep building more sensitive CMB telescopes. Projects like the Simons Observatory and CMB S4 are aiming to measure the CMB with unprecedented precision, especially on the small scales that matter for early galaxy formation. If those experiments find the initial power spectrum doesn't line up with the simple single-field inflation models most people use, that'd be a huge deal, no matter what's going on with galaxy formation. And then you've got dark matter in the mix. There's still a real chance that dark matter behaves differently on small scales than the cold dark matter model predicts. Warm dark matter particles that move faster and can escape from small gravitational wells was suggested as a fix for some small-scale problems, but it also makes it harder for the very first structures to form, which could make the early galaxy problem worse. Self-interacting dark matter, which can clump together more than the usual cold dark matter, might help by trapping more gas and speeding up star formation in those first halos. Untangling all this is tricky business. You need detailed simulations and the growing pile of observations from Webb to really figure out how dark matter and early galaxy formation are connected. Some cosmologists, still a minority, but a growing one, are starting to think dark energy might not be as straightforward as the cosmological constant in the lambda CDM model. That cosmological constant, it's supposed to be a fixed, unchanging energy woven into the fabric of space-time. No matter where you are or when you look, it just sits there, doing its thing. But there are other ideas floating around. Maybe dark energy is actually a field that shifts over time, Or maybe it has tiny bumps and dips from place to place. If that's true, then the early universe might have expanded a bit differently than our standard model says. That, in turn, could have changed how galaxies formed, possibly lining up better with what we're actually seeing out there. Of course, this is all pretty speculative. No one's claiming these alternatives are proven, or even that the evidence really points to them yet. But they're on the table, and it's up to the next generation of telescopes and experiments to figure out if they belong there. Science doesn't move forward by pretending we've already got all the answers. It moves forward by taking those weird, unexpected results seriously and chasing them down wherever they lead. One thing's for sure, this galaxy at Redshift 14.3, it's a game changer. Not because it shattered any big theories or handed us an easy explanation. It matters because it's a clear, undeniable question staring us in the face. In science, good questions are as precious as good answers. The best questions are sharp enough to be tested, big enough to matter, and surprising enough to show us there's still a lot we don't get. This galaxy does all that. At the heart, it's a question about time. What can the universe pull off in 290 million years? Did things really move as slowly as we thought? Or was the early universe a much wilder, faster place than we imagined? This galaxy seems to be saying, look at what I did. I made heavy elements, went through several generations of massive stars, and built up a rich chemical history, all before your models said it should even be possible. Now what? We're working on it. And honestly, that search is one of the most thrilling parts of modern science. So what happens next? Over the next decade, Webb will keep going strong. It's got enough fuel, its instruments are humming along, and it's set to keep peering deeper into the early universe. The list of high redshift galaxies is going to explode from a few dozen now to hundreds, maybe thousands. Patterns that are just hints today will start to stand out in the data. We'll figure out whether galaxies like the one at Redshift 14.3 are rare freaks or just the first ones we happen to spot from a larger group. We'll get better at measuring these galaxies too. More spectra, more chemical fingerprints, more precise timelines for when the universe started making complex elements. We'll finally pin down how many galaxies of different sizes existed at different points in time, which helps us tighten up our models for how structure formed in the cosmos. Then, once the new generation of giant ground-based telescopes comes online, they'll add a whole new layer. Webb is unmatched for faint, distant objects in the infrared, but these 30-meter monsters on Earth, especially with their advanced optics, will let us zoom in on the motions of gas and stars inside early galaxies. We'll be able to tell if they're spinning disks, messy collisions, or something in between. We'll weigh them, compare the mass in stars to the mass in everything else, and just get a much clearer, more detailed picture of what those early galaxies were really like. ALMA isn't going anywhere. It'll keep digging into the cold gas and dust in young galaxies, tuning in at radio wavelengths. Cold gas is the raw stuff for new stars. So, if you want to know where a galaxy sits in its life story, this is what you look at. If there's a lot of cold gas compared to the stars it already has, the galaxy's just getting started. If there's hardly any left, it's winding down. ALMA's data on these early galaxies fits right alongside what Webb sees in optical and infrared together. They fill in the gaps and help us figure out what's really going on. This isn't a one-and-done thing. It's more like a long conversation between telescopes and theory. We get some new observations, knock out a few ideas, tighten up others. Then theorists run new simulations, now using the latest data, and make sharper predictions. Next, the telescopes go out and see if those predictions hold up. Around and around it goes, each loop getting us a little closer to the real story. Eventually, the picture comes into focus. So what will we actually learn when all the pieces click together? At the very least, we'll have a real grip on how the first galaxies formed, how fast they made stars, how feedback worked, how quickly they got enriched, what role dark matter halos played, and how the first light shaped everything. We'll finally understand how the universe transformed from a dull, formless cloud of hydrogen and helium into the intricate, chemically rich place we live in now. That's a huge milestone for cosmology. But there's a chance, just maybe, these discoveries will shake things up in a bigger way. Maybe we'll find out the early universe didn't start off the way we thought. Maybe dark matter acts weird on small scales. Or, dark energy isn't the simple constant we've been plugging into our calculations. If any of that happens, it'll send shockwaves far beyond cosmology. It'll change how we think about space, time, matter, energy, and the wild physics that set the stage for everything we see today. That's the level we're talking about here. Sure, it could turn out there's nothing revolutionary. Maybe new tweaks to feedback or star formation are enough. But there's real excitement in the air, and the possibility of something deeper has everyone's attention. There's something just right about this discovery, coming from a telescope named for James Webb, the NASA chief, who steered the Apollo program through its wildest moments. The Apollo missions were all about people doing what seemed impossible, racing against the clock, using tech that barely existed. Webb's telescope is cut from the same cloth. It's reaching out further than anyone thought we could, seeing things we never expected, and in the process, pushing the boundaries of what we know and what we even dare to ask. Sure, the comparison isn't perfect. Apollo sent people out into space. Webb lets us see the unreachable, using wavelengths our eyes can't catch. But the drive is the same, not settling for the easy answer, building what we need to reach the hard ones, and pushing technology to its limits just to see what's out there. Both Apollo and Webb are proof of that stubborn curiosity, that spark, that looks at the unknown and feels wonder, not fear, ambition, not resignation. And now, this telescope born from that same spirit has found something right at the edge of what we can see. Something that's making us rethink cosmic history in a way that feels genuinely new. This isn't just another entry in a galaxy catalog or one more data point for the pile. This is a discovery that actually changes the game. It makes people stop, rethink, open up new questions, come at old problems from fresh angles. Those are the discoveries that really count, the ones that don't just confirm what we thought, but genuinely surprise us. Nobody saw that galaxy coming. Redshift 14.3, just the number sounds wild. Webb pointed at the Fornax region, and boom, oxygen. Sitting out there in a system so distant and ancient, from a time when the universe was basically just getting started. People expected a faint blip, maybe a curiosity. Instead, they got a headline. That's science at its best. The place where what we thought we'd find collides with what's actually out there. All the real action happens in that space, between modest guesses and reality's curveballs. And this gap? It's huge. Filling it will take years. New technology, better simulations, fresh theories, the whole toolkit. Honestly, some of the ideas we'll need haven't even been dreamed up yet. The folks who'll crack this mystery aren't just working in labs right now. They're in grad school, college, maybe even high school, just now getting hooked by the thrill of big, stubborn questions. That's the magic of a discovery like this. It doesn't just solve puzzles, it hands out invitations. It kickstarts careers, sets the agenda, and gives the next wave of scientists something impossible to chew on. This galaxy will live on in research papers for decades. It'll pop up in every early universe study, the benchmark that every new model has to explain. Progress in the field will get measured against it. And one day, who knows when a paper will finally lay it all out? How this galaxy ended up with so much oxygen so early. The authors will pin down the conditions, name the processes, show how it all fits together. When that happens, the galaxy will shift from being a cosmic riddle to something we understand. But no one will forget the discovery that made that explanation necessary. This galaxy forced us to rethink what's possible. Until then, and probably long after, it stands as proof that the universe is way messier and weirder than our neat little models, 13.4 billion light years away, born just 290 million years after the Big Bang. Glowing with oxygen that, by our rules, has no right to be there, cooked up by stars that lived and died in a frantic rush, somehow finding time the universe wasn't supposed to have given them. It shouldn't exist, but it does. Multiple teams, different instruments, independent checks it's real. That's the real lesson, if there is one. The universe doesn't care about being simple. It doesn't owe us consistency or comfort. For 13.8 billion years, it's been spinning out surprises, no permission asked. Turns out, it's more inventive and more outrageous than we thought. The universe doesn't just last. It creates. It finds loopholes, takes shortcuts, throws us off every time we think we've mapped it out. Every time we've thought we had the story straight, the universe has set us right. Each time we called our picture complete, it threw in a twist. And just when we figured we understood the basics, a new telescope, or a sharper measurement, revealed we'd barely scratched the surface. This pattern's so old, you'd think we'd expect it by now. But somehow, every time it happens, it still feels like a shock, still a true discovery, still that gasp of wonder. Well, this is one of those times. A galaxy sends its light across 13.4 billion years, and here we are, finally able to catch it and piece together its story. That ancient light says, "You thought you had it all figured out. You thought you knew the order, the rules, the timeline. Think again. Look closer. There's more." And it's right. There's always more. So, we look again. We build sharper telescopes. We tweak our models. We teach a new generation of scientists to ask tougher, better questions. We aim our instruments at the coldest, darkest corners of the sky and wait for ancient light to show up, carrying news from the dawn of time. Sometimes, that news matches what we expected. Sometimes, it backs up our models and adds a bit more detail. And every so often, rarely. But it happens we get a signal that's so clear, so strange, so obvious, it makes everyone pause, sit down, and rethink everything they thought they knew. This is one of those moments. A galaxy that shouldn't exist. Spotted by a telescope we only just managed to build. A result nobody really saw coming. Now there's a whole new set of questions, big ones, waiting for the brightest minds of the next generation. This is a discovery in the purest sense. Not just a distant galaxy, but the edge of what we actually understand, and a whole wild landscape of knowledge just past that edge. The universe kicked off 13.8 billion years ago, an explosion of energy and simplicity. From that single moment, through a mess of unfolding complexity at every scale, tiny quantum stuff, all the way up to galaxies, it built everything. Stars, planets, oceans, life, thoughts, questions. It built us. And now, using tools we made, the universe is looking back at itself across time, trying to figure out how it went from there to here. We are the universe, trying to make sense of itself. That galaxy at Redshift, 14.3, it's the universe throwing itself a curveball. The research happening right now, that's the universe working on its own puzzle. And when we get the answer, it'll be one more step in the oldest, longest journey, moving from not knowing to knowing, from darkness into light, from simple beginnings to wild, tangled complexity. It all started 13.8 billion years ago with a burst of everything. It's still unfolding. And honestly, the best parts might still be waiting for us.